بسم الله الرحمن الرحيم. الفريق سمو الشيخ سيف بن زايد آل نهيان، نائب رئيس مجلس الوزراء وزير الداخلية، سمو الشيوخ، أصحاب المعالي والسعادة، الضيوف الكرام، السلام عليكم ورحمة الله وبركاته. اسمحوا لي بداية بالتعريف عن نفسي. اسمي حور عبد الرحمن المازمي، باحثة علوم فضاء في وكالة الإمارات للفضاء، ويشرفني اليوم أن أتولى مهمة إدارة هذا الحوار في هذا المجلس الكريم لمناقشة أهمية البحث العلمي لتقدم الإنسانية وتشكل المستقبل. نستضيف في هذا الحوار البروفيسور ديفيد غروس، عالم فيزيائي وأستاذ رئيس في الفيزياء النظرية والمدير السابق لمعهد كافلي للفيزياء النظرية في جامعة كاليفورنيا سانتا باربرا، حائز على جائزة نوبل في الفيزياء. كما نستضيف الدكتور أحمد عيد المهيري، أستاذ مساعد للفيزياء في جامعة نيويورك أبو ظبي، وأول إماراتي يحصل على قبول للدراسة بعد الدكتوراه في معهد الدراسة المتقدمة في برينستون، حائز على جائزة نيو هورايزنز في الفيزياء. يقدمان اليوم محاضرة بعنوان مستقبل البحث العلمي. ونلفت عنايتكم إلى أن المحاضرة ستكون باللغة الإنجليزية، وبإمكانكم استخدام السماعات لمتابعة الترجمة الفورية. واسمحوا لي الآن من أتحدث باللغة الإنجليزية. Your Highnesses, Excellencies, ladies and gentlemen, it is my pleasure to be here to moderate today's session with our two speakers. This session is titled The Future of Scientific Research, with the establishment of the Emarat Science Council to create a better environment for scientific research in the UAE, and the launch of the HOPE probe under the Emirates Mars mission, to share Mars science data with the world while encouraging research in the UAE on the atmosphere of the red planet. The UAE has been active in encouraging scientific research in order to create a more sustainable future through a knowledge-based economy. But how does scientific research improve our lives? Our speakers today will present to us that link and provide their own experience in the field of science as physicists on the impact of science to improve our lives and inspire future generations to innovate in the field. Please allow me to introduce Professor David Gross, who is the Chancellor's Chair Professor of Theoretical Physics of the Kavli Institute at the University of California, Santa Barbara, and was awarded the 2004 Nobel Prize in Physics. Dr. David.
Well, thank you. It's a pleasure and honor to be here in Abu Dhabi and to address you today on the importance of science.
Please allow me to also introduce Dr. Ahmed al-Meheri, who is nicknamed the Einstein Fellow and is the first Emarati to receive an acceptance for postdoctoral studies at the Institute for Advanced Study at Princeton.
It's a great privilege and honor to be here, and it's also a pleasure to share the stage with Dr. David, my friend and mentor.
It's a pleasure to have you both here with us today. We will start today's session with a question for Professor David. What is the importance of science?
Well, the importance of science, I think, is recognized by everyone. However, there are different kinds of science. A good friend of mine, also a Nobel laureate, said there are only two kinds of science, good science and bad science. And that's true. But people often refer to applied science, technology-driven science, and basic science, and fundamental science. The importance of technology-driven science is recognized by everyone as the search for investigating questions whose answers have ready applications for society is obvious. But why should one support? Why is it important to do what we call basic science, which is better defined as curiosity-driven science, whose questions are posed not by society, not by governments, but by nature itself. That's the kind of science that I pursue, Ahmed pursues, and it is essential. So why is it so important to pursue basic science, curiosity-driven science? Well, the most important answer for at least me and Ahmed is to satisfy our curiosity. All of us are curious about nature, about the world we live in, what it's made of, how it works, what the universe is made of, how big it is, where did it come from. These are questions children ask, and some of us continue to ask all of our lives. In fact, as a species, Homo sapiens, we evolved to understand and control the world around us. And the search for understanding of nature is truly at the core of what it is to be human. And it's the reason our species has been so successful. So, the first reason to pursue curiosity-driven science is to satisfy our curiosity. That's why we do it. But as far as the greater benefit, and that benefits everyone, because my experience is that everyone is curious about nature. But for society, there are many other benefits. I'll just talk about two. One is to promote excellence. So many of the most smartest young kids, young adults, are attracted to basic science because they're curious. They want to understand the big questions about the universe, about nature. And that's what brings them to study what we call STEM, science, technology, mathematics. Basic science benefits society directly by attracting and educating and training thousands of students, some of whom will go into basic science, but many of whom will go into applied sciences and diverse industries. The most important resource of any country are brains. Unless a country can provide opportunities for its brilliant children to pursue their dreams, their scientific dreams, these brains will leave the country and go elsewhere to pursue their scientific dreams. And finally, the most directly important product of basic science is novel technology. And here I'd like to quote the ex-premier of Prime Minister of England, Maggie Thatcher, who said, although basic science has colossal economic rewards, these rewards are totally unpredictable. The greatest economic benefits of scientific research have always resulted from advances in fundamental knowledge, rather than the search for specific applications. For example, transistors, which are at the core of our chips and our modern devices, and the game industry, were not discovered by the entertainment industry, but rather by people working on wave mechanics and solid-state physics and developing quantum mechanics. Nuclear energy, which might someday here replace oil, was not discovered by oil companies with large budgets seeking alternative forms of energy, but by scientists like Rutherford and Einstein, who were trying to understand how the atom worked. Science I like to compare to a tree, with a trunk and roots which represent basic fundamental science, and the branches and the leaves that represent applied science and technology. And one needs a healthy balance. It is, of course, a mistake to just emphasize basic science without the trees, the branches, and the leaves, rather sick tree. But it's also a mistake to emphasize applied science, the tree is not very healthy and eventually will die. What one needs is a very healthy balance between the basic sciences that provide the structure and the fruits are the applied sciences and technology. Basic science, again, is essential because nature is much smarter than we are. And it's much better at posing questions for research about itself. We don't know enough to pose the best questions, but nature does. A good example of this is the famous story about Queen Victoria, who visited Michael Faraday's laboratory, where he was discovering the secrets of electricity and magnetism. And she was very impressed. But then she asked, "This is wonderful, but what is it good for?" And at that time, Faraday really had no idea, and he was an honest scientist. He said, "I don't know. But when we find out, you will tax it." And of course, electricity and magnetism was the basis of the Industrial Revolution and our modern society. And governments taxed it for sure. And this phenomena has been repeated time and time again. The most recent and amazing example is the development of quantum mechanics almost 100 years ago today, where scientists like Einstein and Planck and Bohr and Heisenberg and Schrödinger developed quantum mechanics to understand the structure of the atom. Quantum mechanics replaced our view of the world, and it's very weird and strange, but it works. And we use it to explain the atom, the nucleus, and all of modern physics. The inventors of quantum mechanics had no idea what the applications would be, aside from satisfying our curiosity about how atoms work. That it did. But it also produced the transistor, the integrated circuit, lasers, modern computers. Soon, we hope, quantum computers. The marvels of the applications of quantum mechanics never dreamed of by its developers or by the institutions that supported them have led to our modern technology and the basis of our modern economy. Another great example are medical imaging devices, which prolong our life and help to cure our diseases. MRI, CAT scans, PEP. These devices, all modern forms of medical imaging, started out as detection devices for physics and chemistry, not to help people live longer. That came later, and it was a surprise nobody anticipated. For that reason, Abdus Salam, who was the first Muslim to win a Nobel Prize in physics for understanding the weak, what we call the weak nuclear force, founded an institute in Trieste in Italy called the International Center for Theoretical Physics to promote science throughout the world, starting with fundamental basic science. We're lucky to have two directors of the ICTP here in the audience, previous director and the current director. Salam was really a visionary, one I truly admired. Unfortunately, he's no longer with us. And he said, "It is impossible to talk only of technology transfer, of technology development. One should first talk of science transfer." and technology transfer later. Unless you are very good at science, you will never be good at technology. You'll always be a user and not an inventor. Thank you.
Thank you, Professor David, for the very insightful presentation. So, Dr. Ahmed, can you tell us about your journey and what made you the scientist that you are today?
Yeah. So there are several factors that made me who I am today. Perhaps one of the most important was something that I developed quite early on when I was very, very young. And that's the quality of having the conviction and confidence that something that you can offer, your opinion or your unique perspective, is actually worthwhile to share. This quality is important in many creative fields like art, poetry, and it's absolutely essential for scientific research. I picked up this quality back in first grade, actually. And I remember sitting down in class, playing with some Legos, and I had constructed out of the Legos a Emirati flag. I was just minding my own business. My teacher caught me. She saw the flag, and she was so excited. She beamed with excitement. And she took me by the hand and my flag, and she showed it off to all the students and to the neighboring classrooms. That's when I realized that something that I can make can actually bring happiness or positive change to others. And it stuck with me. It became something very instinctual. The second factor that made me a physicist is something that happened in high school. I was extremely lucky to have exceptional chemistry and physics teachers, Ms. Neda Mansour and Mr. Maroon Abinader. I think Ms. Neda is here in the background. They were both exceptional and clear teachers, clear mentors, but that isn't just the only thing that matters. They taught with a kind of contagious passion. And I would say that's what made science, and especially physics, stick with me. The other thing was that, especially Ms. Neda Mansour, she actually gave us a teaser of a very advanced topic in physics called quantum mechanics that David mentioned. Quantum mechanics is a very advanced subject. It's something that you learn in college. But she would give us a teaser. She would knock on her table and say that the electrons of the atoms of this table have a probability of being on the moon. I thought she was crazy. But then I went on and I learned about quantum mechanics. And then I realized that quantum mechanics is crazy. But then it was too late, I was hooked. So I applied to several PhD programs. And I ended up going to the University of California in Santa Barbara. That's where I met David Gross for the first time as the director of the Kavli Institute for Theoretical Physics. And I would say having the KITP at Santa Barbara was the main highlight of my PhD. It brought so much to the university. The way it functions was that it's more of a conference and workshop center. It brings in people from all over the world, experts, top of the line, doing cutting edge research, brings them all together to Santa Barbara for meetings, conferences, discussing ideas. And you can only imagine how useful that was for me as a student. I would go to these events, soak up as much information as I can, and also give me the opportunity to network with all of these people. by the time I was finishing up from my PhD, I was familiar with what people did in various different places because I got to meet them face to face. Now, the next step after your PhD, if you want to go into research, is to do something called a postdoc, where you get to spend you spend time at different institutions where you're expected to perform independent research. The point is to demonstrate to everyone that you can do significant and creative work without having a PhD advisor supervising you and helping you out. You need to demonstrate that you're independent. I did my first postdoc at Stanford for 3 years, and then the next one at the Institute for Advanced Study for 5 years. The Institute for Advanced Study, or the IAS, is very famous for having had Einstein be there for quite a while until he passed away. And they take great pride in Einstein. The Institute is a very unique place. Everything about it is designed with something in mind. Everything from the office layout to the common rooms to even the placement of the tables in the dining hall are all designed to maximize scientific exchange and output. I would say that my greatest contributions to physics so far happened when I was at the Institute. And now I'm looking forward to growing physics in the Emirates and to contribute to the NYU AD project and more generally for the science project in Abu Dhabi and in the United Arab Emirates. So that's my short story.
Thank you, Dr. Ahmed. So my next question is directed at both of you, but we'll start with asking Professor David. In all the research that you've done, can you tell us about your most significant contribution in physics?
So I suppose it has to be the work 50 years ago that led to the Nobel Prize 20 years ago. And that was the development of the theory of the strong nuclear force. So you know there are 4 forces in nature: gravity, which is still, we don't totally understand at the core. Electricity and magnetism, Faraday, Maxwell, we understand that pretty well, very well. And the 2 forces that act within the core of atoms, in the nucleus of atoms where most of your mass is located. There's the weak nuclear force, that's Salam and his friends, figured that out. And there's the strong nuclear force that holds the protons and neutrons that make up the nucleus together. It's a very strong force. That's why atomic hydrogen bombs are so much more energy and power than TNT. That force was a mystery from early part of the century till the 70s, where it became clear, based on experiments, observation, that these nucleons, the proton, neutrons, seem to be made of, when looked at very good microscopes. Our colliders, our particle accelerators are really microscopes, and when you look at the proton with these microscopes, it looks like actually it's made of strange particles, which people had thought of mathematically, called quarks. But no one had ever produced a quark. They smashed the protons together, quarks never came out. But it looked like they were made of quarks, and that mystery bugged me early part of my career for some years. Finally, me, my student, and another young student discovered a kind of theory which was in retrospect, a kind of simple generalization of Maxwell's theory of electromagnetism that could explain why the proton could be made out of these freely moving particles, quarks, strange particles, when you looked with a fine microscope, and yet they could never come out. That phenomenon is called asymptotic freedom. The fact that in this theory, the force between the quarks gets weaker and weaker when they get closer and closer together, and asymptotically vanishes. That's weird. Normally, bring things together, the force gets stronger. So that theory that developed, QCD, quantum chromodynamics, could explain that, and we could make many, many predictions, which have been now tested for 50 years with increasing precision, thousands of predictions. But it also gave a possible explanation for why you can't pull the quarks out of the nucleus, because the force doesn't decrease when you pull them apart. And if you tried to pull the quarks out of the proton, it would require, according to our yet unproven, but it's clearly correct hypothesis, that it would require an infinite amount of energy, more energy than exists in the Emirates. So that theory is part of what a very successful, rather complete theory of three of the forces of nature. And for the last 50 years, I've been working with the current direction of basic fundamental physics to try to include in this standard theory of elementary particles, the constituents of matter, gravity as well, which is what the younger generation is working on fiercely.
And Dr. Ahmed, can you tell us about your most significant contribution in physics?
So it has to do with gravity, as David just said. And in particular, it was on solving Stephen Hawking's information paradox. Let me explain the paradox. So Stephen Hawking showed, rather surprisingly, that black holes are not the stable, quiet objects sitting there hiding in space. What actually happens in a black hole, if you take into account crazy quantum mechanics, they actually gradually shrink and evaporate away, emitting a kind of radiation out of them. Eventually, they wink out of existence. What Stephen Hawking noticed, however, was that the nature of this radiation coming out of a black hole doesn't depend on how the black hole was formed or what it was originally made of. The information of anything that falls into a black hole completely disappears from our universe as the black hole disappears, leaving only the radiation. What my colleagues and I showed, and which got us the New Horizons Prize, was that if you study the radiation more carefully, actually you can recover the information inside a black hole. But it's a very hard or difficult or complicated procedure that you're going to have to do to the radiation to actually be able to read what fell into the black hole. In fact, this hardness, or the way that the information is encoded in the Hawking radiation, surprisingly follows things that we are familiar with from a very different context, from quantum computers. So in a quantum computer, the most basic element is the qubit. So you have a collection of qubits in which you store some information, and then you can process it in various different ways. But the reason why it's so hard to build a quantum computer, the reason why we don't all have one, is that the quantum nature of particles or of these qubits is extremely sensitive, and it can be easily disrupted or even just completely removed through its interaction with the environment, with noise from the environment. And so there have been various techniques developed for building a quantum computer in a smart way that has a kind of error correction where you encode the information in a collection of qubits where the relevant information is encoded in a very complicated way. Hence, only a complicated interference can recover the information. Any simple interference would not recover the information. And it's in this way that the information in the radiation knows about the interior. This connection is so deep that there are actually gravity-motivated quantum computer architectures. I make no statement about how useful they are, but it's just very interesting that you can have proposals for how to design quantum computers from gravity all the way in the other building. And so I really think it's a very interesting time for research in theoretical physics. And this feeds back into what David was saying about the lines between the different disciplines getting more and more blurry.
And to follow up on that, with all the work that you've done on black holes, can you explain to the audience in simple terms what they are and how they are important?
Black hole and simple? Okay, I'll try. All right. So the way that a black hole forms is when you put enough matter or energy in a sufficiently small region of space. When that happens, it triggers an instability of space-time. Einstein taught us that space-time is a thing. It can get deformed, it can get bent and evolve with time and so on. What happens in this instability is that space-time crunches into itself and then at some point just ceases to exist. Okay? You might have heard of the term the singularity, the point in the center of the black hole. So that's not how I like to think about it. And in fact, in most black holes, the singularity is not a point in space, the center which you can point at, but the singularity is actually an end of time. Okay, there's a board here behind me. I'm going to try to use it. So let's imagine that this entire board here represents space-time. What I mean is that time goes upwards and space goes sideways. All of you here are not moving in space, but you are moving in time. So if I was to plot your motion, you would just be a straight line like that. I was sitting down and then I got up to this point. This means that I was not moving, and then I moved a little bit, and then I'm standing again, standing still. When you have a black hole, when space-time becomes unstable and ends, what happens is that there's a region where the space-time just ends. That's the squiggly line here, but it continues outside of the squiggly line. You might have also heard of the event horizon of a black hole. That's the point of no return. If you pass through it, you cannot come back out. The reason why you can't come back out is because you end on the singularity, the end of time. If you are outside the black hole, you can make it far away from the dangerous region. And that event horizon is something that looks like this. The region the wedge, if you will, that if you enter, you cannot make it out again. In some sense, a black hole is something like an unstable and collapsing bridge. Imagine that you're trying to cross a bridge, and then suddenly it starts to collapse. Depending on where you are on the bridge, you might be able to make it to the other side or not. The point on the bridge where you would make it or not make it, that's like the dotted line. That's like the event horizon. That's the simplest explanation of a black hole I can provide.
My next question is, what do you think could be the future of science and scientific research in the UAE? And we can start with you, Professor David.
Well, like many questions in science, I don't know. It depends on you. I'm talking to you. I'm very impressed with last time I visited Abu Dhabi was maybe 10 years ago, maybe a dozen, the Festival of Lights. I'm really very impressed at what's going on now. It's amazing. I'm very impressed with the NYU Abu Dhabi effort and your dreams. There's enormous potential, clearly, enormous resources. You're in a very interesting niche in the world. You have enormous opportunities and dreams, ambitions, resources, but I think it mostly depends on your leaders, your brilliant people. I hope for the best, but you have enormous possibilities ahead of you and enormous ambitions and resources. So the future could be very, very bright indeed for science in the UAE.
And Dr. Ahmed, what are your thoughts?
Yeah, now that I'm back here, I'm thinking very deeply for how I can contribute to physics in the region. And something that I feel, well, my plan is to try to develop science by leveraging on the local resources that we have here in Abu Dhabi and in the UAE in general, and also to use the UAE's extremely strategic location. Here we have India. Dr. David spoke of ICTS, that's located here. There's another famous and well-regarded institute in Mumbai. These are actually sister institutes. There are also institutes here. Very famous institute, the Weizmann Institute for Science in Israel. And there's a big gap in between. In fact, there is so much interest and support for connecting these two different groups and the region, so much so that, in fact, there's a conference that I've organized here at NYU Abu Dhabi with the support of NYU AD Institute and the UAE Space Agency, and it's happening as we speak, bringing together 40 of the top minds in theoretical physics, and all of that gives me great optimism for the future.
And for my final question, what scientific question would you really like to know the answer to? We'll start with Professor David.
That's a very difficult question, since there are so many questions I would like to know the answer to. You know, I always say that the most important product of knowledge is ignorance, which sounds paradoxical, and I don't mean the bad kind of ignorance that leads to racism or war, I mean the ignorance that the fact that the more we know, the more we understand that what we don't know, the questions that we can now ask. And there's so many of them. But if I had to choose one, it would be the origin the beginning of time, the origin of the universe. How did the universe begin? Now that is a question that everybody asks and has asked for centuries. But until recently, it was a question that was not a scientific question, not addressable by the scientific method that I outlined. It was addressed by philosophers, by religious authorities, but not by science. Today, it is beginning to be addressable by the scientific method. We can probe observationally to the very early, maybe even seconds after the universe began, whatever that means. And in fact, we're challenged by these observations to go back further and further where all of our theories, especially of gravity, break down. But this is a new kind of question for physics, and therefore very challenging. Physics has never been able to even imagine providing an answer to that question. How did it all begin? What does that mean? How could time begin? So I'm confident that science will answer that question. I would love to be around to know the answer, but I'm pretty confident that Ahmed will be around to find the answer, to know the answer.
Dr. Ahmed.
I would say I agree with Dr. David that is perhaps the most interesting question about what happened at the very beginning. It's a very hard question, difficult question, because not just for the reasons that David mentioned, but also because it depends on everything we know about physics. It's a place where everything we know needs to be put together in order to be able to understand. In some sense, my investigations into black holes is a step in trying to understand the beginning of time question, because inside the black hole, something very similar happens, but in the reverse. Time ends. And so the hope is that by understanding better and better what happens near the singularity as time ends, we can understand what happens in the reverse when time begins.
Thank you, professors, for your answers to my questions and for your valuable insights. في الختام، تناولت المحاضرة اليوم أهمية تنمية العلم الأساسي لتغذية العلم التطبيقي، ونبذة عن طبيعة البحث العلمي وأهميته لتقدم الإنسانية. شكراً للبروفيسور ديفيد غروس وللدكتور أحمد المهيري وللحضور الكريم ولصاحب المجلس حفظه الله، والسلام عليكم ورحمة الله وبركاته.